Okay, this is the tangent line approximation to a curve, and you're going to do it a lot. It's kind of a precursor to something we're going to do next semester, which is really exciting. But you can see here that I have graphed f of x equals square root of x, and I went ahead and took the derivative and wrote the equation of the tangent line. So it was y minus 2 equals 1/4 the quantity x minus 4, and that was after taking the derivative and plugging in 4. So at my point of tangency 4, 2, where it has a nice little bullseye there, if you look at right around that point, and I'm going to draw a picture right around that point, it's hard to tell where the curve and the line really separate. It's true that the only point that they actually intersect is at the point of tangency, 4, 2, but if you stay really close to the point of tangency, you can see that the line is not a bad approximation of the curve. So if I wanted to know what the square root of, let's say, 4.2 is, I could use a tangent line approximation. So here is the point 4.2, the point 4.2, square root of 4.2 is on the blue curve, and if you plug 4.2 into the line, you're not going to see much error. So once you have the equation of the tangent line, you just go y equals 1/4, 4.2 minus 4 plus 2. So here we get 2/10, and so 1/4 times 2/10 plus 2, and we get 2 and 1/20. Not a bad approximation. If you put that in your calculator, you're going to see that we're really close to that. So that's one example of approximating at a tangent line. So the first thing you do is you just define the function, find the point of tangency that is closest to 4.2. So in this case, that's why I chose the point 4.2. If I wanted to know what the square root of 10 was, then I would have used the 0.93, knowing that the further you get away from the point of tangency, the less accurate that your tangent line approximation is going to be. That's pretty much the gist of it. Here's one other thing that's kind of cool. I'm looking at this and I can clearly see that the line is above the curve. So I know that 2 and 1/20 is actually greater than the square root of 4.2 because my tangent line lies above the curve. If you've got a picture, that's easy. If you don't have a picture, you have to rely on concavity. So anything that is concave down, the tangent line is always going to lie above. And anything that's concave up, the tangent line will always be below. So suffice it to say, we may need a second derivative here. The first derivative, which I didn't show you, is 1/2 x to the negative 1/2. The second derivative is negative 1/4 x to the negative 3/2. And for all values of x in the domain, which would be greater than 0, your second derivative is always going to be less than 0, concave down. Therefore, tangent line is above. And if the tangent line is above, the approximation is greater than the actual value. If the tangent line is below, the approximation is less than the actual value. So that's how to do a tangent line approximation to a curve. On the front page with where I talked about dippity-doo-die, I'm going to do an actual word problem in a minute, but down at the bottom, we were using differentials to approximate values. And so I wanted you to approximate the square root of 10 using differentials. Instead of using differentials, first, I'm going to do the tangent line approximation. So I identify the function as square root of x, because we're taking the square root of 10. Hopefully you see that. then I'm going to actually find a value that I know the square root of. So that would be 9. F of 9 is 3. So without drawing the picture, I'm going to use the 0.93. So my derivative, which is 1/2 x to the negative 1/2, plug in 9 into the derivative to get my slope, and I get 1/6. And so my tangent line approximation is going to start with y minus 3 equals 1/6 times x minus 9. So that's the equation of the line. I know that it's going to be close to the curve as long as I am close to the point of tangency. So y equals 1/6 10 minus 9. So here I am putting this value in for x, plus 3. 10 minus 9 is 1 times a 6 plus 3 is 3 and 1/6. And that's my approximation of square root of 10. That's not going to be as good of approximation as my square root of 4.2, mainly because I'm 1 unit away from my point of tangency with 10, and I was only 2/10 of away from my point of tangency using 4.2. So the object with differentials, and you're going to get the very same answer, is to take the equation y equals square root of x and pick a point very close. So when x is 9, y is 3, and when x is 10, what is y? That's basically what I'm looking for here. What's my change in x between 9 and 10? dx is 1. And really what I'm looking for here is what is dy, so I can add that on to 3. So dy equals 1/2 x to the negative 1/2 dx. So dy is 1/2 1 over the square root of 9, which is 1/3, and dx is 1. Again, I get that dx because the change from 9 to 10 is 1, and I get my change in y to be 1/6. So because 9 plus 1 is 10, 3 plus change of y, 1/6, is 3 and 1/6. And that's how to do the problem with a differential. If we're working with an object that has a formula other than like just taking cube roots and square roots, like we have with the die on the first page. So you've got a die whose volume is s cubed. And we know that we would like for the dimensions to be 5.5 millimeters, and that would be our desired size. But we're okay as long as the side only varies as much as plus or minus 15 hundredths. So we're going to take the differential, so dv equals 3s squared ds. And then we're going to plug in 3 times 15.5 squared times, and I'm going to leave the plus or minus off, but I'm going to put it in my final answer. So if you multiply all that out, and I didn't bring a calculator, so hang on. Three times 15.5 squared times 15 hundredths is 108.113, and that would be cubic millimeters. So if we're off by as much as 15 hundredths on every side, that means that the maximum amount that we're going to be off on a cube of 15.5 millimeters is 108. And we're going to put the plus or minus on there. So if you are 15 hundredths too much, then you're going to be 108 and 113 thousandths too much, or too little, if your each dimension is too little. Hopefully this makes sense, but we will go over it again on Friday. Good luck on the, how many problems? 6 problems on the back page. If you have questions, you know where to find me.